Morning, dear colleagues. Let's start our morning session. It's my big pleasure to introduce our first speaker, Sergei Yurievich Dobrokhotov. This is the title of his talk. Please.
Okay. So first of all, I would like to thank organizer for possibility to come to this beautiful place and to give a talk here. And so it is actually our common work, which was done with Kalinichenko, Minenkov, and Nazakinsky, and actually it is a part of our big work connected with the solution of the shallow water equation and its application to the tsunami waves. Moreover, I would like to say that it is not, this work is not finished yet, and it is maybe the main fact which I would like to attract your attention is some mathematical problem. Okay. So I would like to maybe to attract your attention to one problem which is seems to conjecture. It seems it's true, and I will try to compare this result with some experiment which was done in our institute. And but first, I would like to remind. I spoke about this problem many times. It's not the first. I mean, in a global, from the global point of view. But some point I will stress when we come to it, which is rather new and not finished yet. So our problem is the consider the shallow water. Не работает, да? To the shallow water equation. Maybe. Не, микрофон работает, указка не работает. Ну ладно, хорошо. Ну, здесь. So this shallow water equations, it is quasi-linear system which appears in many physical problems in water waves and plasma and so on. And so we want to consider the special Cauchy problem, which we call the localized initial data. So mu, which you see here in the second formula, is a small parameter which actually characterizes the size of the source, and so we have the parameter when we use for construction, which we use for construction of physical sense. It's a shallow water equation. So the global equation is a Euler equation here, but in the water layer. But if we consider the long wave, the long with respect to the depth, then eta, yes, okay. So thank you. Eta is free elevations, and U is two-dimensional vector. So it's two-dimensional problem on the plane. The D is characterize the depth. So this is J is the axial gravity. So this is the shallow water equations, and the main object which usually the people are interested in, it is free elevation. Of course, velocity is also useful to construct. So the fact is that if you consider the long wave, especially tsunami wave, that in the open sea, you can linearize it, and instead of the nonlinear system, you obtain the linear system, which if you separate the so-called wave mode and the vortex mode, then it includes both phenomena. Then you can, for the wave mode, you can obtain the wave equation, which you see on the right part of the slide. So the mu, as I told you, this is the characteristic size of the ratio between characteristic size and the characteristic size of the basin. So mu is actually small. For instance, if we consider the tsunami wave, then standard tsunami wave has about maybe between 100 and 30 kilometers, and the size of the ocean is 2,000 or 1,000 and so on. So this is a small parameter actually. Okay, then the goal is to construct this asymptotic solution of this problem. Oh, I'm sorry. Then actually we ocean is not the infinite layer. So we have the shoreline, the beaches, and actually we want to construct the solutions on the bounded domain, and it is, you see, on the right side, and that is give many difficulties to construct the solution of this problem, because we have the free boundary problem near the beach, because the boundary changing. See, so that is the one of the main problems. Also, it's a big problem because for the numerical, accurate numerical analysis, because there is no standard boundary condition. Even in linear case, you see, you have the boundary conditions, and so instead of them, you must add, if you after linearization, you must add some assumption about the self-adjointness of this operator, linear operator, for instance, into wave in the wave equation. And Aleynik and Radkevich, and many years ago, showed that it's in this case you can the classical boundary conditions which people use should be changed by the boundless of energy, and then it is the conditions for the uniqueness and existence of solution. So okay, then so there is there is a lot of papers about that. I just present some of them, and it's so we have some big reviews, and soon there appear the review in Russian Mathematical Survey with the long paper, and so you can find many over here. So, but I just want to say that it's important for us. It's a work of Carrier and Greenspan, which appeared many years ago, connected with the nonlinear shallow water, one-dimensional shallow water with sloping bottom, and then also many interesting facts was discovered by Pelinovsky and Mazova, and but also in multi-dimensional case, even in one-dimensional case, we use this just recently the idea of Fock about the quantization of canonical transform. Then it's some other papers connected with the semi-classical approximation. Of course, there's the books of books of Maslov and Maslov-Fedoruk, and the people who belongs to their schools. Okay, so what is the difficulty? No, I told you and repeat that in the one of the main difficulties is the boundary. In non-linear case, it's no standard boundary conditions. Yes, it's so also. And the second case, it's even if you linearize the problem, then there appear many for this problem there appear some singularities like caustics, and we call them non-standard caustics. So in this case, for instance, the leading front edge, this is the non-standard caustics, and the second is the beach, the shoreline also is non-standard caustic. And so it's necessary to, if you use the semi-classical approximation and this apparatus which called Maslov canonical operator, it should be, we need to modify it very seriously. So it's okay, but I will speak about it. Then what we can do if we will analyze the problem, Then it exists the general Maslov scheme. So first we need to present to rewrite our equation in the form of differential observed differential operator. I speak about very briefly. And we can present in this case or general case our original equation in the form of differential observed differential operator with a small parameter, which could be mu or maybe some other parameters in our. And then if we present a solution in the form of this Maslov canonical operator, and it's possible to do, and in this case it's trivial. The next step is not trivial. But then we can construct the asymptotic solution using the general scheme, and it is based on the fact that first we must pass from the quantum problem, or the problem with the partial differential equation, to the dynamical system, to the Hamiltonian systems. It is in the case of the system, then it's not scalar. Okay. Then we have not one Hamiltonian, classical Hamiltonian, but the set of Hamiltonians, and so they denote them lambda j. And so there is so-called known like effective Hamiltonian, and so assumption which we use that they are not intersect, which was used early, that is not, they are not intersect. It means that the mode does not intersect in this case. But it's not, so that is a global idea, and we use it for construction the solution, but after some modification. Then what is the general scheme? So first we must construct so the initial data connected with this the geometrical object in the phase space, which is known like a Lagrangian manifold. It is lambda 0. Maybe it's not see here. It is on a canonical operator. Yes, and then you must do the following. You must shift this Lagrangian manifold according to the Hamiltonian system, which are the eigenvalues of this matrix valued Hamiltonian. And then after shifting, you shift also the initial data and add some integral over those trajectories, and then you lift this object in the classical mechanics, lift to the to the quantum or partial differential level using this canonical operator. So you have the canonical operator first, which defined on the manifold lambda 0, and then after the shift you construct a set of Lagrangian manifold, and then you summarize them, taking in account some geometrical object, topological object like Maslov index, and so on. So the solution will be, it was done under assumption that all this lambda 0 does not, this Hamiltonian, effective Hamiltonian do not intersect. How this scheme connected with this our problem? So it is very simple and trivial fact that if you consider the initial data with a small parameter h or mu in this, so it could be associated with the Lagrangian manifold, which is no more but a vertical place in the phase space. So it is just, we fix x is equal to psi. Psi is the point when we have the localization of our initial data, and p is belong to all the to Rn. It's an n-dimensional case. So then we have such a formula on the third here, this formula, and then after realization of the construction, it should be, we hope that we construct the solution in the form of the sum of this canonical operator. It is a long story, and it is a lot of papers connected with this thing, but what is the one of the some remark that if we take the amplitude A, which are fixed on this initial Lagrangian manifold, is no more but the Fourier transform of the initial data, but in not original variables, but in variables x minus xi divided by h. And but if this A tends to 1, then this solution could be present the asymptotic of the green function. It is not maybe the strict statement, because it's a lot of some additional condition and so on, but we must use them. It could be used in special problems, but it's additional work, big additional work and many problems. Because what does it mean, the green function and asymptotic of green function? I remember the story when we discussed this, the green function with Misha Shubin many years ago, and he asked me, what do you mean when you speak about the delta function? It's not the function, it's a functional, yes, and you must add the space where it acts and so on, and its asymptotics could be true for one space and it's absolutely not true for the other space, and it is still, this problem is open, you see, because it's, if you change, especially if you change the parameter, then you can make big mistakes in this asymptotics. But for the localized function, this is a condition actually, what kind of function we say, that is, could be proved in okay, so what is the for the wave equation? What we some example how we construct the solution in linear case. So the asymptotics based on the very simple Hamiltonians, which is modulo p, c of x. P is a momenta corresponding to x, so p1, p2. But we see that it is not smooth in point of p equal to 0. That is why the direct using of Maslow's scheme here is not could be modified, you see, because we have a singularity, and the singularity corresponding to the long wave, because the small momenta means that we have considered long wave, and our problem connected with a long wave. So it's and first when we began to start to do to work with this problem, it was maybe 40 years ago. We used the not a scheme, but of course we take it into account. But then, very recently, maybe 2 or 3 years ago, with Andrei Shafarevich and Vladimir Nazaikinsky, we constructed a new version of canonical operator. It looks maybe not so elegant like the classical one, but it's covered this case also. So it is. So the scheme is also work. So what is when we say? If C is equal to constant, then you see first we have the Lagrangian manifold, which was the vertical place. Then after shift, this Lagrangian manifold transform to the half of cylinder on the half of plate. And so it is so first of all, what is that? It's project on the curve, closed curve in the circle. That means that what is the caustic from the point of view of Lagrangian manifold? It means that your projection is not one-to-one map. So, and here we have very strong caustic, because all the manifold projected on the closed curve. And so this is a strong caustic. Moreover, sometimes it could appear some other singularity. I will show you but a new formula which we have, which we construct, it works in this situation. And I have no opportunity to speak about it because it's not the main topic of my talk. But we have a new type of Lagrangian manifold. So it's not a new type, but they are not considered before because it's a singularities, not a singularity of projections, and like in Arnold and Varchenko and Gussein's other book, but it is real singularity of the manifold. And so it's how to work with them. It is a lot of problems. So this problem shows that it's not the artificial one. See, so then okay. So then we construct this Lagrangian manifold, and so I What can be in the other situations? In the more, if the depth is not is not constant, then you see then for all the waves over the underwater bank. So what we have? So this is the race, the red one on the left picture, and then the blue lines is the this projection of this singular Lagrangian manifold over fronts. So the solution at each moment of time localized in the neighborhood of this blue line. But you see, first there looks like the circle, but then after some time could appear some new singularities like cusps, and but it is strong caustic, you see. So it is so the Lagrangian manifold you can see on the right side, and see in the near the tails of this cusp you see what kind of the solution is possible also construct using these formulas. Our formulas, we construct solution on in this case, and it is what the solution near the cusp, the head of the cusp. You see, then what is interesting to stress that due the jump of the Maslov index when we cross the trajectories, then the structure of the solution is also changed. So there appear on here you see that there appear something like the ridge and underwater ridge. You see some overtake it, how to say it is like a well, something like that. Yes, because the Maslov index jump. So it is okay. Now that is one of the formulas which is based on our construction, and so you see that includes all the object. That's no more but no less. You see it? So it includes the relationship. This is the free elevation. It includes the initial data, initial perturbation. This is the f function f, which is a Fourier transform of initial perturbation, and then it includes the Jacobian in semi-classical analysis, which actually here is separated into parts. We have the and the first part is connected with the so-called divergence. So if x psi, it is a coordinate on the front. So it's equal to 0. We obtain the additional on the caustic. We obtain additional more large singularities, and then we have the so-called green law, which give us relationship between the wave on the initial point and the on the point of observation. So so this is the formula which give, as I told you, no less but no more. But then interesting fact that so it is the simplest formula, but important thing for application to find some more effective formulas, and the fact that is only for some very narrow class of initial data you can also simplify it. And one of the very beautiful source you can see on the left in the low part of the because it is a so-called what was suggested by Datsenko, Sergeyevsky, Cherkasov, Vank, Lamahita, and maybe now we found that it was presented in the book of Sretinsky many years ago, but then he think that is not important, and in the next books he eliminated it. But it's actually very interesting, and it plays a very important role, because when you even test some asymptotics and numerical analysis formulas, then it's you see the solution near the front is presented in the form of the f of s. It is just algebraic function, Moreover, it's possible to differentiate it and obtain very wide class of initial of interesting Okay, so now what is about the second type of caustic? So it is a beach, and then the Hamiltonian in the wave equation is now the Hamiltonian is preserved on the trajectories, and so if we see the Hamiltonian h equal to modulo p c of x is equal to c of 0 for our problem, then p tends to infinity when d c tends to 0. Yes, so it is a beach. It means that, as I show you here before, as d is equal to 0, it's also this asymptotic doesn't work. In this case, it means that we have a new type of caustic. So this is a new type of caustic, and moreover, we have in our problem, we have interaction between the caustic which is connected with the leading front edge and with the beach. So, and this is a problem. And here, so in one-dimensional case, you see this is trajectory could be drawn in such a way. And here it is necessary to use comptify this problem. Yes, and then after the variable p, we introduce the new variable p equal 1 to c, and then instead of the manifold with the singularities on p, you see this is a manifold singularities on the momento. So instead of it, we have this move manifold like on the right side, and it is there in the two-dimensional case when we have such type of pictures when the front comes and reflect from the beach. So, okay, then this change of variables in two-dimensional case, but it's not only in two-dimensional case. I think it is very recent paper, so I have that is possible to use not only for water waves but in elastic waves and so on, because if we have the layers which, for instance, I don't know, granite and then basalt and then the mat. So we have such type of effect. So we have the reflection and then the caustic. Again, caustic, then the amplitude there is larger than over there. So we construct the canonical transform, which make comptification of the problem. And then after that, we use the for quantization remark that each canonical transform implies in quantum mechanics or in equations of the partial differential equations imply the integral transform. It is he presented, this idea belongs to Dirac, and he presented in his book, and Fock, I think he translated his book, and then he began to study this problem and solve it, and he published it in several papers, but also he, in preface to the Dirac book, he present his this analysis. It is very useful in this case, and it is so it's also, of course, it's very interesting. This is water waves and quantum mechanics, and then met in this case. So the formulas which we have should be presented in such a way, and so it's a new representation for a Maslov canonical operator. It was some ideas in a simple case which was realized by Vladimir Savelich Buslaev many years ago, but in more simple case, and unfortunately he died before we obtained this formula, and I cannot discuss with him this. We cannot discuss with him. So again, if we use this special initial perturbation like this, then the Cauchy problem could be, then the solution near the cause could be, in linear case, could be presented in a simple form, no, more or less effective form. So it is again the algebraic function, and so it's possible to analyze this solution in the near the beach, but if the front have the simple singularity. Okay, now what the problem, now let's pass to the nonlinear problem. And the problem is that the problem, what assumption which we did, so first the shoreline is a smooth, and then it's the normal derivatives, the normal derivatives is not equal to 0. So it is more or less sloppy beach. And then, okay. And then in non-linear case we have the, as I told you, free boundary problem, and is this the main problem in this situation. Moreover, you see, it's we solve this problem in linear approximation, but maybe from the point of view application, maybe the one more interesting case is part of the work is the run-up or splash of the waves, and linear theory doesn't give it. Yes, so it's not necessary to use the non-linear case. And so what I remind you what is the Carrier-Greenspan transform. So let's consider one-dimensional shallow water equation. So again, this eta is a free elevation, v is velocity. And so we consider the case then d is approximate or exactly equal to the linear function. So the depth means that the bank or the shore means that x equal to 0. Then the Cauchy problem, which we consider in this case, is some localized initial data which comes to the shore and then reflected to it. It was so. But what is the very beautiful observation and the fact which was proved, maybe in not such a form, but it is more general maybe form, because they constructed a solution and actually they didn't present in such a form their transformation. But that is the transformation, you can check it by hand, you see. So what is this? First, let us linearize our initial equation. Linearize not in like in a inverse scattering problem, but like naive linearization. We omit non-linear terms. Yes. Then we obtain linear shallow water equations, and then we can consider the system of passage from the old variables tau, from the linear variables tau and y and y to the non-linear variables x and t in such a form. And then the theorem is the following. If this transformation of coordinates is not degenerated, then the solution of the original nonlinear problem on the low part could be presented in a parametric form in the using such formulas. You see, on the second from the low part. So very, very simple fact, but very useful, you see, because it's just a student of the second year could check it. You see, it is not okay. So no, that is some repeat. Then what the theorem? So actually, what is could be how to extrude. So we can construct the transform, and then on the low part you see this exact solution. So if Jacobian is not equal to 0, then we can use this transformation. Okay. Then what also? But what we what was our observation? So our observation was the following. So actually we can, in this transform, we can omit this two. So this is maybe the main part of my talk. You can forget about which I spoke about earlier, but this is maybe one of the main idea of this talk. So you can omit these terms. Yes, of course it was not the exact transformation, but when we use this initial data and check the solution, you see that the solutions without this velocity and with velocity, their difference is very, very small. So red and black. And so it means the idea that in asymptotic sense, we can omit this velocity. Yes, and just construct the transformation, change the Carrier-Greenspan transformation, simplify it, and to present it in such a form. Rho is a cutoff function which is working near the bank, near the shoreline. In the open ocean, it is not important because it's just a linear problem. But here it is non-linear problem, and so we can construct this type of so this is the this transformation, and then moreover, when we check the Jacobian and the breaking of these waves, it looks that the majority of the waves without breaking. If breaking, then the Shilovot equation is not working. Yeah? So we can the Jacobian is equal, almost equal 1 to before the breaking. So we can use, instead of the more or less, no, it is of course a simple, but we can simplify it and omit this velocity. So then, what is we see? That first, that this transformation could be generalized for the two-dimensional case. There's no problem, you see, because it's a very simple transformation. Of course, it's parametric form, but then the second fact that after this transformation, we can rewrite our equation, non-linear equation, in two-dimensional case and one-dimensional case. We can rewrite in new variables, and then first we get the fixed boundary. There is no free boundary now, yes? And the second, that if you consider the non-linear terms in this after reduction, you see that they are more or less small if there are no breaking. So if we consider the parameters, so I don't want to stress you with that, but that means that the leading term of after this transformation give us in leading term give us the linear problem. And so the algorithm, first we solve linear problem and then come back to the using this inverse transform, which is simplified Carrier-Greenspan transform. Of course, it's possible to use some iterative process like method of iteration, and then so one of them is possible to see. Okay. So that is the algorithm for the two-dimensional case. Also, I think it's not complicated to just learn formulas, but it's just a generalization of the two-dimensional case, this procedure. So it is what formulas are followed. And this is so first we solve the linear problem, and then using these formulas we obtain the splash and the run-up effect in the non-linear problem also. So generally we obtain, finally we obtain this type of algorithm. First we have the initial data, then we construct the rays or trajectories which come to the point where we have the observation. Moreover, it is our problem which was done together with our friends from Igor Nosikov from Kaliningrad, Igor Nosikov, and Maxim Klimenko and Anton Tolchenikov, which could be, they suggested to use the variational method for construction of these rays, and it is very fast algorithm. So I would like to say that it is, first, it's more stable than the Hamiltonian system, and second, that we don't construct the solution with the, I forgot in English, пристрелкой. When the many trajectories start from the one point, and then we choose just one which we need. But here we just fix the first and the second, and then we construct the trajectory. So this idea was used not only for this, for instance, for the tunneling problems and so on, because it's they have really fast working algorithm. Maybe it's some open problems, but nevertheless it's possible to do. And then first we solve linear problem, then near the bank we use this Fock quantization, Carrier-Greenspan transform, and so on and so. But we have some formulas and some algorithm, but of course it's necessary to work for realizing in a real situation. It's much more work. So, but now I would like to say that this idea, which we use here, it is not strict mathematical one. So it is necessary to use some more general, more strong apparatus, like the theorem of сжатых отображений, something like that. But it is very recent, so it is our plan. But if somebody join us with it, we are not specialists in this situation. But it's very beautiful work. So what we can do also, but all, of course, this simplified Carrier-Greenspan transformation could be used in one-dimensional case. And so we have the experiment at our institute to verify it. So the experiment is connected with the problem such a basin we have, and then there's the whole standing wave. So this periodic solution of the non-linear shallow water equation. So it's connected also with the seiches. So if the seiche, for instance, in Baikal, and that's so we can replace the two-dimensional phase from the one-dimensional case, and so we have the long waves were known as seiches. So we have such a vibration stand in our institute. So it is a big. The sizes, it is in Russian, да, размеры сосуда 50, они дальше, наверное, будут, да, так, я что-то их пропустил. So it is about maybe 70 centimeters and about 20 centimeters on the wide, and so it is the sosud and the vibrate. Then if you the parametric resonance. If you catch the wave, the resonance, then the wave would be. And so we use this experiment. So this is again there's some works connected with this paper, and so maybe I do something wrong, and I didn't add the paper of Izolda Viktorovna Sturova and her colleagues from Novosibirsk. Maybe I put these slides in another presentation. So what we have here, so we construct the one-dimensional case in the basin with such a bottom, and then we have very recently we obtained with Nazaikinsky very simple formulas for in this situation, connected also with the Fock transformation like near the beach. And so this formula you can find here. It is not in linear situation. Okay, then so another maybe also type of basin. First, the left part is so it is like an angle, but we have from on the right we have the wall, and so here we have the additional condition like. The derivatives of equal to 0. So we have several problems. It is because interesting to compare it with the real experiment, and then so this experiment, it is the slope, the plane depth, yes, and so we have this is this standing water, but it's after this experiment we understand that the amplitude so small if we have no breaking. That is not good example for experiment because it's breaking, and or if we use the small amplitude we don't see anything. So then we so what kind of solution we can construct in general case? So it's just something like the Bogolyubov averaging method, Bogolyubov-Krylov averaging method. So we have non-linear periodic solutions, and so the amplitude and the frequency change and depend on the amplitude, but the amplitude is so small that this change is not big. But nevertheless, it's possible to use this scheme. We started but not finished yet, and so this is some formulas for the solutions. And now what is the but nevertheless, the leading term is again the linear wave, but after that, we use the inverse carrier green span transform and obtain the nonlinear solutions. Again, I would like to say it is just the physical work. It's not the strong mathematical. It's open problem. And so if somebody wants to work with it, it will be very nice. So, and what we see. So this is the linear situation. The linear situation, it is blue wave. But we can construct a solution just before the bank. Okay, 2 minutes. Yes, and then after this Fourier carrier green span transform, we obtain this curve. So, and again, the same we have for the other type of words. Then, so this is again some experimental done, and this, but what? So after this plane bottom, we find that it's better to use the the bottom which is not plane, and moreover we use the bottom which is a parabolic function. And in this case, the solution of linear problem is exact solution is based is expressed in terms of Legendre polynomials. So it's very good solution for the experiment. Now, what is the experiment? You see, so here this is the waves, and what is the? See, so we have. That's almost no breaking. You see. So, and what is the? This is my light slide. This is the comparison of exact. Exact is the points, and the continuous line is our formulas. You see, here you have more or less good, It's coinciding. Yeah. So, yeah. So it gives our hope that this mathematical construction is true, and so it is. Could be used not only in the one-dimensional case, but in multi-dimensional case. We have no Latok in our experiment, so it's possible to use. So this is again. So thank you. Thank you very much for your attention.
Thank you very much for your very interesting talk. Are there any questions?
Сергей Юрьевич, спасибо большое. Maybe in English, this approach to shallow water equation.
Yeah.
We have two directions previously.
Yeah.
Before the Babbage and ray expansion and so on. And the second is exact solution. We can write fundamental solution for shallow water with and singularities. We can write precisely, and then integrate every kind of sources. And your approach is somewhere between, as I can understand.
No, I see that first the Babbage he can, of course he works with semi-classical with rays analysis, but he doesn't work with the problem with localized initial data. Of course he can construct a green function, but it's different, you see. And then also I would like to say that I repeated many times that the direct solution of the problem with the localized initial data is much more constructive and much more effective than the use of the green function. Because what's that, the green function? It's not a one function. It is a family, because it's the initial data depends x minus xi, and then you integrate over xi. And so to construct numerically on some construct a green function, you must consider the lot of rays starting from the different initial point. We construct just trajectories from one point. Then you have the additional problem of integration. It's not very simple, you see, because the integration, especially near the caustic, it's a lot of problems. And up to now, there is no good theory how to do it. You see, because it's because you need to use something like the Weierstrass preparation theorem. It's you like a Malgrange theorem, and no, they're not constructive. Of course, you can use the numerical analysis, but it's I think that's you must use much more time to use. So to construct a solution with a localized solution in one point, of course you must, in a tsunami wave, you first must, using the inverse problem, you must find this point. But we have some experience and some method how to do it using this work with our colleagues, and so we continue to do it. Yes, but then I think that from the point of view, even from the numerical analysis, it is more effective. You see, because it's. And also, I would like to say that the Babbage and then many others, they didn't do it because it's just a recent work. So I spoke many times in seminars on St. Petersburg among his colleagues and so on, and many also in France and so on. So there is a new formula, a new approach. And nonlinear also, it is very trivial, yeah? But it's some mathematicians said observation. We find the exact solution which can be used for the numerical experiment, not numerical, but in mathematical. Just you move the cursor and you see that a very good coincided with the simplified solution in this one. So this is.
Спасибо.
Thank you.
Are there any other questions?
So, first of all, thank you very much for beautiful talk. And maybe the following question, is it possible to say in popular terms in which situation we can expect tsunami waves?
No, you see, that is the tsunami wave. This is a very wide problem. So, but and also it's the formulas which we present the local one. So in the beach, if the beach or shoreline is smooth and the sloping bottom, not vertical, then it's possible to use in this case. So it's possible, but it is just some mathematical first step. You see, that to realize it, it's necessary to use to do much. You see, it is in our plan, and so, but it is, you see, it is intersection, Hamiltonian system, Fock transformation, Carrier Greenspan, and so on. And each of these directions require a lot of force to be realized. Okay.
Thank you very much.
Thank you. But if somebody want to join us in this case, we will be very glad. You see. Moreover, we have somebody with some project, and so it's money, and so it's not. No.
Okay, thank you very much. Thanks again. So we will start in 7 minutes. Владимир Вячеславович, вы с нами?
Да.
Отлично. Здравствуйте.
Я только не могу понять, как мне демонстрацию экрана включить.
Сейчас попробуем разобраться.
Здравствуйте. Вот вы как раз все, мы вас видим. Теперь сделайте Ctrl-L на компьютере у себя.
Ctrl-L на компьютере. Не работает.
Ctrl-L не работает у вас, да?
Да.
Просмотр нажмите, вот просмотр наверху. Файл, редактирование, просмотр.
Наверху.
Файл, редактирование, просмотр, подпись, окно, вот где вкладки.
Сейчас пока я не вижу, где это наверху. Наверху чего?
Ну вот вы в Acrobat, в Adobe Acrobat зашли, у вас наверху вкладки файл, редактирование, просмотр, подпись, окно.
Да.
Вот, просмотр.
Куда вы говорите?
Просмотр нажмите.
Просмотр нажал.
Так, вид страницы.
Вид страницы, да?
Так, где у вас? Ниже еще. Полноэкранный режим.
Да.
Вот, нажмите.
Нажал.
Вот, мы вас видим хорошо. Все, теперь... Все,
прекрасно.
Да.
Коллеги, уже пора начинать. Владимир Вячеславович, вы в Бразилии, да, наверное?
Нет, я сейчас в Москве.
В Москве. It's my big pleasure to introduce our next speaker, Vladimir Vyacheslamovich Sokolov. This is the title of his talk.
Thank you very much for the opportunity to give a talk here. The title on the screen. Now we can see several references. What I want to stress, almost all papers are very recent. Something unpublished yet. Now the main subject of my talk is integrable matrix differential equations. First of all, let's start from the example. Let's consider the following system where A, C, and B are numbers, I is identity matrix, and U and V are M by M matrices and known M by M matrices. And I claim that this system is integrable for any size of matrices, M. This is scalar if M equal to 1. What does it mean to say that this is integrable? This is integrable in all reasonable senses. For example, it has a Lux pair. It can be integrated by the inverse scattering method. But for us today, integrability means that the equation or system has infinitely many conservation laws or first integrals. So for any m, this system has many first integrals of motion. If m equal to 1, this is a scalar system. This is Hamiltonian. And the Hamiltonian is cubic. We see that if we consider the level of Hamiltonian, we will have here the elliptic curve, and our system defined a dynamic of the point on this elliptic curve. In the general situation, the metric situation, it's still Hamiltonian, but the Hamiltonian function is not these polynomials, but trace of these polynomials. Now this is a matrix, and trace is a Hamiltonian. And this is typical situation for integrable matrix systems. The first integrals has a form trace of some non-commutative polynomial. It's a typical situation. So now let me say several words about why matrix models, matrix differential equations are important. I can say two things about this. First of all, even the simplest integrable matrix models inside has sometimes very non-trivial integrable models. Let me show the example. In the previous case, let's put C, A, and B equal to 0. So there's a simplest matrix model, UT equals to V squared and VT equals to U squared. But inside of these integrable models, but what's important is that the size of matrices is arbitrary. And inside of this simple model, we can see this, for example, namely, if we consider the difference of U and V and find the eigenvalues, such, in this case, the square roots of eigenvalues satisfy to the following Hamiltonian, big Hamiltonian, M is arbitrary, a big Hamiltonian system. Francesco Calogero very likes such models, but this model was found by Inozemtsev. I am not wrong. This is a rational version of Inozemtsev integrable model. And this is very typical situation, so-called reductions. You consider something related to the integrable matrix model, and of course, any reduction is also integrable. It's the first reason. And the second reason is related for me with recent papers by Sasha Mikhailov. He developed a procedure how to quantize a classical integrable model, not Poisson brackets, not any structures, but directly integrable model. You have classical integrable model, and he claimed that we can apply the following. First of all, we want to find the matrix generalization of this model. Matrix, or if you want, you can consider U and V as generators of free associative algebra. And if you find this non-commutative generalization on the free associative algebra, after that, the second step, you can try to find the commutator relations which respect the dynamic. And if you find this, you have integrable quantum integrable models with commutator relations, and so on. And this approach works in several examples. I like this activity. So this is the reasons. There are several reasons more, but for me this is enough. Okay, now the main idea. My talk is devoted to the first part. I want to explain how to find the matrix generalizations of integrable, scalar integrable polynomial models. The first remark is that the integrability means that the equation has some additional structures, something like Lax pair or high symmetries or conservation laws and so on. And first, I want to say that all these structures can be generalized to the matrix case. Today, we will play with first integrals and conservation laws mostly, but also the Plenary approach to integrability of scalar models can be generalized. If I will have time, I will show something. But let's start from the conservation laws and integrals. As I already said, the general form of the first integrals is written here. It's a trace of some polynomial depending on unknown matrix variables. So rho is a non-commutative polynomial dependent on matrix unknowns, and we can find trace. But if you want to work not with this, but with the polynomial itself, how we can rewrite this? We can rewrite this in the following form. Of course, if we take trace, the trace of commutator is 0, and we will have this. So if we want, we can say that conservation law is a non-commutative polynomial such that the t derivative with respect to our matrix system is the sum of commutators. We can use this for computations. It's a constructive definition. Now, this is about ODEs, about PDEs with two independent variables, like Korteweg-de Vries equation and so on. In this case, we have the following local conservation laws. The t derivative of trace not 0, but it's the x derivative of trace. What does it mean? This is formalization of the following identity. If we consider the following functional, this means that t derivative of this is 0. Now, not function is t independent, but functionals. But formally, this is a local definition of conservation laws. In the case of two independent variables. And again, if I want to play with not traces, but with the polynomials rho and sigma, they are non-commutative polynomials, we can write the following. Of course, if we take trace from both sides, we will get this. But in the computation, this is the identity of the local conservation laws. Now, this is the main idea. The main idea is the following. If we have a given differential equation and some additional structures related to integrability, then we want to find the matrix equation such that if the size of matrix is 1, this should coincide with this first. And second, these equations must have the same additional structure generalized to the matrix case. maybe this is not clear, but now I want to consider an example. If the example will be understandable, it's more or less all what I can explain, can try and explain here. What I want to say before example, that this approach turns out to be very efficient if this equation is polynomial, say homogeneous polynomial here, and we want to find the homogeneous non-commutative polynomial instead of E bar. Let me start from the well-known integrable model, modified KBV equation. It has infinitely many conservation laws. The first conservation laws for this equation has the following density. Rho, this is the densities, and I don't want to show sigma. You remember that the conservation law is a pair, rho and sigma, such that t derivative of this is x derivative of something. But this is two simplest densities of conservation laws. Suppose I want to find the matrix or non-Abelian. Sometimes I use one term, sometimes another, but for me today, no difference. Suppose I am speaking of matrix generalizations. I want to generalize this to the matrix case. First of all, this is a homogeneous polynomial. Homogeneous if you have weight 1 and x differentiation with respect to x only, also have the weight 1, it's 4. This also weights 4. So it's a homogeneous differential polynomials. I want that in non-commutative case, it will be also homogeneous differential polynomials. And if I want this is the maximum what I can write. Of course, instead of this, I have 3 different possibilities because now u and ux not commute with each other. And also this term has a weight 4 with a known coefficient. So I want to find 4 numerical coefficients such that this is integrable. And if I want that in the scalar case, if the size of my matrix is 1, it should coincide with this. This means that the sum of these coefficients is 6. So actually I have only 3 unknown coefficients. First of all, and I want also that all conservation laws, all conserved densities, scalar, they also should be generalized to the matrix case. I want to find the non-abelization, not only the equation itself, but also all this sequence of conservation laws. So let's start from the first density. I want to write instead of this trace of the matrix polynomials. And it's clear that this matrix rho is just this, what I want. I want that this coincides with this if the size of matrix is 1. But it's easy to see that this is the only what I can write here. Now I use the fact that this is conservation law, conserved density for this, and the simplest computation by hand, I would say, not by computer, give us that this is the density for this equation if and only if K3 plus 2 K2 equals to 6. So I have one linear relations between coefficients more, 1 and 2. So I have 2 coefficients only. And now I try to use the matrix generalization of this conservation law. What I can write instead of this, trace of what? it's a non-commutative polynomial such that it coincides with this. And this is defined up to commutators and up to total derivative. Of course, if I add commutator to here, trace will annihilate this. And the total derivative, as usual, will go to the right hand side, dx of sigma. And you can verify immediately that the general form of the polynomial, non-commutative polynomial, which goes to here under the scalar limit, is just this. We see here two parameters, unknown parameters, z and y. We cannot kill these parameters by subtracting of commutators and so on. So now we have two parameters here known and two parameters in the conserved densities. And the computation by computer, probably by hand it's a bit complicated. We will have the following system between our four unknowns, two coefficients in equations and two parameters in the conserved densities. This is non-linear system, and it has two different solutions. It's very trivial to solve it. So we have two different matrix generalization of the modified KdV equation. The first solution corresponds to this, and the second corresponds to this. I need to some scaling to kill I, but this is two different matrix generalization, integrable matrix generalization of the scalar modified KdV. If you use a scalar, of course, both of them coincide with the standard modified KdV equation. They are really integrable because the Lux pair for both were found, if I am not wrong, in this paper by Khalilov and Kruslov. Actually, this activity about matrix integrable models, Marchenko was one of the first who started this. I can show the references, and this is the people around him at this time. And what I can say more, you can ask why in this generalization we think that K2, K3, K4 are scalars, constants. What if we try to write here constant matrices? I don't know, here, 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 and everywhere. I can only show one example where we have an arbitrary constant matrix, not scalar constant. It turns out it's a recent observation from our paper with Seewadler that this is integrable. This is generalization of this, of course, but here we have additional terms with arbitrary constant matrix. Well, sometimes it happens, but this trick with first integrals work very efficiently. You have seen this. In the case when the coefficients are constant, about scalar constant, about matrix constants, I will say several words after that. So this is the idea. And I can try to implement this for different integrable scalar models. And for me, this is still a miracle. Why almost all polynomial integrable, scalar integrable models have some matrix integrable generalization. Sometimes one equation has several non-equivalent integrable matrix generalization. Now let me show one experiment more. Let's consider the following system of ODEs. Now we are about ODEs. where Z1, Z2, and Z3 are arbitrary constants. And actually, this system has two first integrals. And for some special values of these physical values of these parameters, this is Euler top for three-dimensional Euler top, which describes the rotation of rigid body around the center of mass. But from mathematical point of view, algebraic, I would say, point of view, these parameters are not essential. We can kill them by scaling. And in the next formulas, I will think that they are normalized by 1. And now I want to generalize this to the matrix case. I want that U, V, and W be M by M matrices. What I can write, which ansatz I can use for this? First of all, now I don't know the order of variables here, so I can write this with unknown k. If the m equal to 1, this is just uv, and also there are some unknown commutators. So I have 12 unknown parameters. And that's all what I can add because of the homogeneity of the right-hand side. I still try to keep the homogeneity. And what I now can use, you remember that our scalar system has two first integrals. And now I want that, and of course, any power and any product of these integrals are still first integral for the scalar system. But now I want that all these scalar integrals has a non-abelian, non-commutative generalization, such that if the size of matrices is 1, our non-commutative, our matrix trace first integrals coincide with this. You use only several small I and j, and immediately get that the constants are no constants as here, for example, k1, k2, k3 should be 1/2. So this is a symmetric situation, and only 3 commutators, 3 parameters under the commutators survive. So this test gives me the following candidate for integrable matrix Euler top, I would say. How to prove that this is really integrable model? In this case, sometimes the simplest way is to find the Lux pair for this. Of course, I can try to prove that for any I and j, we have a matrix generalization of these first integrals. It's true, but I prefer to find the Lux representation. I was successful. Here I found some Lux pair. I can, let's skip it. So this is really integrable models. Now let's let's play a little bit with matrix PDE integrable systems. Again, the same approach. This here is our joint paper with Seva Adler. We start from non-integrable polynomial models of this kind. Actually, the famous nonlinear Schrödinger equation is here. If we write the nonlinear Schrödinger equation as a system of 2 equations, we will have something like that. And there is a complete classification of integrable models of this form. Let me show you the result. You can find all these lists in the papers by Mikhailov, Shabat, and Yemilov, but you need to work a little bit. Know these lists directly, but at any rate, there is the following integrable scalar models. This is the first list. I will explain the difference. So this is just nonlinear Schrödinger equation written as a system, and there is 5 systems in this list. I want to stress that in the last one, we have 2 arbitrary constant parameters, alpha and beta. Actually, by scaling, we can kill one, but still one parameter is here. And the second list is the following 4 equations. What is the difference? We call the first list nonlinear Schrödinger type systems, and this is the so-called Boussinesque type systems. On the level of the Lux pairs, here the Lux pairs are in the SL3, and for the first list, they are in SL2. On the level of first conservation laws, the orders of sequence, all of them has an infinite sequence of conservation laws, but the orders of these conservation laws are different. Here there are some gaps in the orders, so they are really different, and we want to find a non-commutative generalization for all equations from this list and for all equations from the first list. And here, and we use the same trick as I start with modified Cauchy equation. And the result is given by the following table. No explicit formulas. You can find these equations, they are equations in our paper, but what we can see here, S1 is just this, nonlinear Schrödinger. There is exactly one non-commutative generalization, well known, but for the second system, there are 2 different, and so on. So here we have we can see the number of different generalization. For example, this has 3 different generalizations. But what is interesting, in the scalar case, you remember in this model we have 2 parameters, but not for arbitrary alpha and beta we can find the generalization. Only for 3 sets of parameters there exists such non-commutative matrix generalizations. It's interesting that exactly these two sets of parameters well known in the scalar situation. They have some names, I don't remember. Levy, and this is some, I don't remember. Maybe Gedrikov and somebody, but not for, let's fix, not for any alpha and beta, there exists a matrix generalization, only for several. Now the list of Boussinesque type systems, we see that the first has no local generalizations. Yeah, and here 1 and here 2. Now let me show several explicit formulas. First of all, here there are some 2 non-commutative generalization of what? as for this system. There are two different integrable matrix models just here. Of course, U and V are matrices, and if the size of these matrices is equal to 1, this is just our scalar models, both. And we proved that all our generalization we found in our table, all this stuff, they are really integrable. We found the Lux representation also. For example, for these two models, this is the Lux representation. So actually, this is a zero curvature representation, and this is potentials, depending on lambda. But we can skip this if we don't want to know about Lux pairs and zero curvature representations, but it was proved that all these models are really integrable. Now let's go to possible classifications. In the previous cases, we start from the known integrable scalar model, use the same trick. We generalize not only the model itself, but also this stuff like conservation laws or first integrals. But this is classification of integrable matrix system of this form. So let's consider the simplest homogeneous system of two matrix models. Alpha 1, 2, 3, 4, and betas are unknown constants. We want to find all sets of constants such that this is integrable. I will explain in which sense integrable. We start to play with this class of matrix systems with Sasha Mikhailov 20 years ago, more or less, and found several different examples. If you remember, I started from one of such models. There it was inhomogeneous, but in homogeneous case it was ut equal to v square and vt equals to u square. Now I want to find all possible integrable models of this kind. And I want to use the same trick as before. It was trick for given integrable scalar equation, I found the matrix generalization. So I want to start from a bit strange question. Suppose we have a scalar system of this form. How to find all integrable models of this form? For the first glance, this is a stupid question. Why? Because this is a homogeneous system. If I divide 1 by 2, I have homogeneous ODE. And we know that it can be solved in quadrature for any sets of constants here. But this definition, this is not definition. If you want to say that integrability means that you can integrate this in quadrature, first of all, it's not clear a bit, but the most important problem, I cannot generalize this definition to the matrix case. And I need a definition of integrability which I can generalize to the matrix case. This is the main idea. I will generalize the definition of integrability and I will trace, okay, but if you have a general, say, quadratic system of ODEs, usually they use two classical objects related to integrability. First is the first polynomial first integrals. You remember some histories about rotation of rigid body, Kovalevsky case, and so on. Additional first integrals, polynomial first integrals. This is the first object which can be generalized to the matrix case. And second, again, related to these problems is so-called Plenary property. Let me start first from the first integrals. I am both. I will call this system integrable if both it has a polynomial first integral, and second, it satisfies two Plenary-Kovalevsky test. I will discuss this a bit later if I will have time. But first I want to formulate the statement about the scalar case. If our system has a polynomial first integral, in second it satisfies the Kovalevsky-Lyapunov test, then there are only 5 different possibilities for the first integral. Let me a bit explain. We want to classify this not exactly, but up to equivalence. Of course, if we find the linear change of variables, we will get a similar system with different coefficients. And in the matrix case, we have also the transposition as the equivalence transformation. But in the scalar case, we have linear transformations. And up to linear transformations for integrable scalar systems, the first integral can be reduced to the following 5 different forms. So I use the linear transformation not to bring the right-hand side to a canonical form, but I want to normalize the integral. And what I can say more about integrable models here. If our scalar system has a first integral, then it has infinitely many polynomial symmetries. It's commuting flow. Here we can put any first integrals, and this is trivial remark that this dynamic with respect to commute with the initial scalar system. You can say that this is trivial because if you fix the value of integral, this is just our scalar initial scalar system, nothing more. It's true, but if we go to the matrix case, it does not work. This formula does not work. And to find the integrable matrix generalization, we postulate that our integrable system, first, of course, it coincides with the corresponding scalar system, and second, it has matrix generalization of all this hierarchy of polynomial symmetries. It works. We don't need the whole hierarchy. We need only several n to find all things. And now we have some lists of integrable models. Not exactly integrable. They are suspicious to integrability, but we should prove somehow the real integrability. But for example, we can find such set of models. I can show several examples from this classification. If we consider the scalar equations with this first integral, this is case 1, it has 3 different generalizations to the matrix case. This is the ansatz of generalization, and it turns out that there are 3 non-equivalent sets of alpha and beta here, 3 integrable models of this kind, and we found all this generalization for all 5 different possible first integrals in the scalar case. There is also some generalization of not homogeneous. It's more or less trivial. If we have homogeneous integrable models, it's not difficult to find the possible linear tails such that this is still integrable. And one of these models is just the model I started with here. Okay, so now I want to discuss, I have several minutes, a different definition of integrability. Namely, I want to speak about the Plenary tests. Actually, according to Plenary, the ODE equation or system is integrable if the general solution has only movable poles as the singularities in the general solution. Movable means that for different initial data, the position of pole could be different, but no real singularities, but only poles. How to use this definition for constructive calculations, how to find integrable models using this definition, or how to check that a given model is integrable. We can use so-called, we call this Plenary-Kovalevsky test. What does it mean? Suppose we have a standard ODE of ODM. The general solution of this ODE have m arbitrary constants. But we, of course, we cannot solve this. We cannot, but we can try to find formal solutions, say, of this form. This is Laurent series. The sum starts from some negative part and plus Taylor. If you take any, you find this, but I additionally required that first the position of pole is arbitrary, this arbitrary constant, and that the coefficients contains m-1 arbitrary constants more. I want that in this formal series I have m, maximum number, m of arbitrary constants. And I require that the formal Laurent solutions have maximum number of poles. It's a strong requirement, and this is somehow relates to the initial Plenary requirement, no movable singularities, only poles. But this is more or less simple computation. If you have a given equation, you substitute it to here, find the coefficients one by one, and see how many arbitrary constants you have in the Laurent solution. For example, the most trivial example here, let's consider the following ODE. If you substitute such ansatz to here, you first find that L is 1, and you can find first term equal to this, and all additional Taylor tail is identically 0. So you find the exact solution without any infinite. And here you have one arbitrary constant as we want in the general situation. Why I start from this trivial example? Let's try to do the same, but with the matrix equation. Now the same equation, but y is a n by n matrix. How many arbitrary constants we will get here, and how it works? What is the difference? If I want to find the Laurent solutions and count the number of arbitrary constants here. We start from the same story, but now C are constant matrices. And I substitute it to here, and what I can see? First, I see that the residue here. No, first I see that the negative part here is just when k equal to -1. So we have the Laurent term matrix multiplied by z minus z to the power -1 plus Laurent plus Taylor tail. And first we find that the residue, the leading coefficient, satisfy to this algebraic relation. It's trivial, follows from the equation. And after that, second, we will see that any next coefficients will be found from the same, more or less the same relation. Here something known polynomial. And to find the next, we should invert the linear operator. K is just this K, its identity, and the operator is given by this formula. It's the operator from matrices to matrices. C minus 1, this is just our residue. And when we will have some arbitrary constants in the coefficients, only we have the chances. First of all, we have several constants here in C1. And here we will have a chance to find some arbitrary constants, only this is not invertible. Some degenerations. So K should belong to the spectrum of L, the first. And second, this is, in this case, this is inhomogeneous system of linear equations, something, conditions like Kronecker-Capelli theorem should.
Владимир Вячеславович, время уже.
Yeah. And in this case, I need 1 minute more. In this case, we will find from analysis of the spectrum of this operator, we will find the spectrum is -2, -1, and 0. And here K should be not negative. So we calculate here and we find the first, the Jordan form of this matrix is, I can say, this should be the matrix of the rank 1. Only in this case, we will have a chance to find the n square constants. And second, we verify that in this case, really we have m square constants in the Lorentz solutions. And in this case, we can solve this equation exactly. This is the solution. And we can see why the residue should be a matrix of rank 1. You see, this is a generic solution, and the pole we have only in the eigenvalues of the constant matrix here, and the Taylor expansion of such function has such matrix has a matrix of rank 1 as a residue. So, and after that, this is just simplest example, but we can play with this approach for different integrable models. And in our paper with Seva Adler, we found all integrable in this sense already, in the sense of Pinlevé test, all integrable generalization, matrix generalization of the famous Pinlevé 2 equations. There are 3 different integrable models. Now we are working with Pinlevé 4. The result is already obtained. So that is my talk in some sense. It was a survey of the results obtained by this moment, but I hope that several simple ideas were clear. If not, it's my fault. So I can start here.
Okay, thank you very much. Thanks. Are there any questions? Sergey Vladimirovich.
Thank you very much. For applications in inverse problems, your test example is very interesting. A matrix Riccati equation. Are there any publications concerning the...
No, about Riccati equation, no, because it's more or less trivial, but I want to, if I will write some review to the subject, I will add this. But this is Riccati equation without right-hand side, pure, homogeneous. It's trivial, but maybe you are right. The investigation of matrix Riccati equations with right-hand side, it should be interesting.
Thank you. And the second question, if you consider some kind of convolution, Toeplitz matrix, non-linearity like Toeplitz matrix, are there any results or ideas?
You mean, I call this reduction. You consider not a generic form of matrices, but something additional, like skew symmetricity or Toeplitz structure. Yes, of course, this work, but I never tried. This is very recent results, and I have a feeling that there are a lot of interesting unsolved problems here.
I think so. Thank you.
Okay, thank you very much again. So we have coffee break for 15 minutes.
if you can, but I am going to be present.
Игорь, вы можете...
No, now voice and visibility is okay. Alexander can talk himself.
Игорь, вы можете запустить презентацию?
Да, еще раз добрый день. Сейчас собираются, и я запускаю презентацию. Только вы не говорите, пожалуйста, хорошо в Zoom, потому что вас тоже будет слышно. Я запускаю с компьютера, который у меня идет Zoom. Я запускаю, и, соответственно, вы потом по окончании презентации тогда уже можете задавать вопросы и общаться.
Хорошо. In some minutes we will show your presentation.
Thank you.
And please turn off your microphones. And after presentation, we can discuss.
Yes, sure. I'm going to be here. Good morning to everyone. I would like to thank the organizers for the very kind invitation for me to talk in this important conference. I also would like to greet Professor Hasnov and everyone in the audience. This talk is about the determination of mechanical sources that act over beams, plates, their assemblies, spider webs, by the use of almost periodic distributions. The theory of almost periodic functions was inaugurated by Harald Bohr in the beginning of the 20th century, and he considered the closure of the following set of trigonometric functions, which then he called the set of almost periodic functions. We show applications of almost periodic functions and distributions to the solution of inverse problems involving human-made structures such bridges, buildings, ships, planes, and also an application to a natural structure, which is the spider web. We start by calling the attention to the importance of the theme structures. It suffices to say that Galileo himself dedicated half of his book Discorsi Dimostrazioni Matematiche intorno a due nuove scienze to the analysis of the failure of a cantilever beam. Also, we can recall some disasters that happened recently. For instance, in India in 2018, in France in 2018 also, a bridge in São Paulo City, Brazil, in the United States, in Brasilia, in Brazil, February 2018, in Genova, Italy, also a catastrophic failure of a bridge. In Italy also in 2020, in Mexico City recently in 2021. We also have a catastrophic failure involving a cable that snapped, but also we had problems involving a brake that didn't work properly. Many of these catastrophic failures involved the death of many people. But what's a structure? A structure essentially serves to preserve the shape of systems, and it's very fundamental for the survival of this system. The system can be natural or human-made. Structures are intrinsically involved with loads. Essentially, the structure receives loads, then transmits loads, and discharge loads to external supports. Loads can be essentially of three kinds. Can be point loads, line loads, or distributed loads. All these loads can be modeled in Sokolov spaces, negative Sokolov spaces. Besides external forces, we also consider internal forces. internal forces, they appear as a result from the fact that the material tends to resist deformation. And the internal forces, they manifest themselves as normal forces, shearing forces, or moments. There are many books and references about internal and external loads in simple structural elements, but I cannot not mention the works of Timoshenko and Landau and Lifshitz. They are reference works very important in the field. The main structural elements are the cable, the rod, the beam, and the plate. The rod can resist normal forces but traction forces. The rod resists normal forces but can be traction or compression. The beam resists essentially bending moments, and the plate is the analogous of the beam but in 2 dimensions. These are the equations for these structural elements. This is the bar equation, the Euler-Bernoulli equation for the beam, and for the plate we have the Kirchhoff-Love equation. Now I talk about the works related to the identification of forces in single beams. These works then can be roughly classified into those that use information concerning the final state of the beam, final displacement or velocity, into those that use information concerning the displacement over an arbitrary small part of the beam for an arbitrary small interval of time, and into those that regard a static problem and look at the shape of the beam to identify the load that causes that shape. And just to mention the works that use spectral methods. These methods, they are more related to the identification of properties of the beams themselves, such as area or moment of inertia. Since they are applied to the identification of these coefficients and not of loads, I'm not going to talk about them here in this presentation. I just would like to mention some very interesting and relevant works due to Barcelon, due to McLaughlin, Gladwell, and Morassi. Regarding the works that deal with the problem of identification of loads in single beams, I would like to mention the pioneering work of Professor Hasanov and this very recent paper from Professor Hasanov, Professor Romanov, and Professor Baisal, where they consider the identification of the spatial part of the load in damped beams. They proved that the identification of the spatial part of the load is possible under some conditions relating the final time when the final observation is taken, the damping coefficient, and the temporal part of the load. As for the works that deal with the identification of loads acting over single beams, one considers a small part of the beam observed for an arbitrary small interval of time. I mention the works of Niquez and Madame Zaire, and in this particular paper they considered the identification of a finite sum of point sources, and the data were obtained from measurements on the boundary of the beam. The methods that they used were based on contrariability results. Other works that I would like to mention, which are based on almost periodic distributions, which were written with Professor Hasanov and Professor Morassi. they use the information obtained from an arbitrary small part of the beam for arbitrary small interval of time, but they also work when we use data obtained from the boundary. There is another class of problems where one considers the static problem of the beam. The beam is loaded by a force and the displacement is measured. From the measurement of the shape, by using regularization methods, the load is identified. I would like to mention the work of Collins that used data obtained from a strain gauge. The strain gauge essentially measures the deformation of the beam along its length. I also would like to mention this work of Professor Lesnik, although it's not related to the identification of loads over beams. He made a mathematical analysis of an essential engineering problem for the identification of a coefficient of a beam when one considers the shape of the beam when pre-established definite known force acts over it. The works in engineering that are related to the identification problem of parameters and loads are so vast and so varied that entire presentation dedicated to them would be necessary just to cover a small part of it. The difference is that in engineering the works tend to focus more on discrete systems based on matrix methods. A work that I would like to mention is this one by Udvadia and Sharma that appeared in the Siam Journal of Applied Mathematics. Here they analyzed a building and treated it as a discrete system, but it was done in a mathematical style. Now I talk about results for single plates. The history of the development of the equation for single plates is very interesting, and it can be found in classic references for the history of the strength of materials, such as written by Timoshenko or by Todd Hunter. The equation that was obtained originally by Sophie Germain and Lagrange was later put into a larger framework by Kirchhoff and Love. So today this equation is known as Germain-Lagrange or Kirchhoff-Love. For us that are interested in inverse problems, I mentioned the works of Professor Yamamoto, and in particular this one where he proved that the spatial part of loads of this form, which is a product of a spatial function and a time function, the spatial part of the function can be identified when we know the information regarding the displacement of a line that is parallel to one of its sides. Madame Zaire also worked with rectangular plates, and she proved that linear combinations of Dirac's delta distributions can be identified when we have at our disposal data obtained from measurement on the boundary. Since unique continuation properties can be very useful as ingredients in the proof of uniqueness for the identification of loads acting over plates, I would like to mention just two works. One is from Professor Kim and the other from Professor Isakov. Both use Kalman estimates. In this paper written with Yamaoka, we consider polygonal plates which possess eigenvectors that can be written as trigonometric polynomials. We proved that for loads of the form that has a form of a product of a time function and a spatial function, the spatial part of the load can be uniquely identified when we observe a small, arbitrary small open set for an arbitrary small interval of time. As for unbounded plates, we have this result. Loads that has the form of a product of a time function and a spatial function. This spatial function can be identified when we have observation made an arbitrary open set in time and space, and this load can be any distribution with compact support. Now we talk about assemblies of simple elements. We start with assemblies of simple beams. Now we consider a structure like this, showing this figure. The beam is simply supported at each one of its supports, and it's loaded with a distributed load F. The equation that governs the system is this one. The displacement is of class C1, and we remark here the load that has this special form. This is a product of time function and a spatial function, and also that the second derivative at each one of its supports is 0. Physically, it means that the moment applied at each one of these nodes is 0. That is, the external torque applied at these points is 0. Also, the displacement at its support is 0. Since we impose that the solution must be of class C1, we automatically are saying that the slope at each one of its sides of a support is equal. This is a problem with immense interest for engineers, because making measurements of the displacement at one place of the structure, it's possible to identify the load everywhere in the beam, as it was proved with Professor Morassi. The measurement can be made on an arbitrary small open set in time and space. We note that the identification is possible even across internal supports, which means we measure the displacement at one place and we get enough information to identify the load everywhere. It means that enough information flows across internal boundaries so that unique identification is possible. There is, from a theoretical point of view, no minimum value for the time interval, the length of the time interval for making the measurements. This is because in this model the velocity of propagation of signals is infinite. But in practice, of course, the longer the observation time, the better the identification. And of course, the more information we get, the better we evaluate the probability of the failure for this structure. So that's why this problem attracts much attention from engineers. Now we consider a system of assemblies of plates. An assembly of plates is like this, shown in the figure above, where several plates are joined together along lines. But just to simplify the mathematical analysis, we consider just two plates juxtaposed, joined along a line. The equation that governs the dynamics of this problem is this one. This is a simply supported plate, meaning that at the boundaries the displacement is 0 and the second derivative of the displacement is also 0. Along the line that joins the two plates, the displacement is also 0. We impose the existence of the first derivative at both sides of the plate, which in this case implies that the first derivative is the same from both sides of the line that joins the plates. We assume that the load is of this simple form, a time function multiplied by a spatial function f. The function g is assumed to be known, and we want to identify f. We remark that due to the boundary condition of this problem, it's practically difficult to obtain information about the problem from measurement strictly taken on the boundary. Therefore, the meaningful problem is to inquire if the unknown load F can be identified from internal observations. It means that, in physical terms, we want to know whether the presence of the constraint imposed at the line that joins both plates prevents enough information to flow across it, so that identification is impaired. The result that we reached is that if we have data obtained from an arbitrary small open set in time and space, then we can identify the load that acts all over the plate. That is, we can identify the function f, which is the spatial part of the load, if we have the information concerning the time history for an arbitrary interval of time of a small open set of the plate. Now we present a system of assemblies of bars that occurs in nature, which is a spider web. However, we postpone the presentation of this structure to present some material concerning almost periodic functions and distributions. Harald Bohr is considered to be the founder of the theory of almost periodic functions. He published 3 very important papers almost 100 years ago, between the years of 1925 and 1926. There is a book written by Bohr himself, Almost Periodic Functions, published by AMS. A more modern and comprehensive exposition can be found in this book by Constantin Cornet-Anon, Almost Periodic Oscillations and Waves, published by Springer. We have a characterization given by Bohr. We consider a continuous function, a positive number epsilon and a number tau, such that if the difference between ut plus tau and ut is less than epsilon for all t, then tau is called a translation number of u corresponding to epsilon. Now, for Bohr, a continuous function u is called almost periodic if for every epsilon positive there is a length L epsilon, such that for any interval of L epsilon, this interval contains at least one translation number tau of u corresponding to epsilon. Bohr showed that the space of almost periodic functions in this Bohr sense is equal to the closure in C0 of the set of trigonometric polynomials written like this. With Professor Zinn, we have a work in which we studied the properties of almost periodic distributions in the Bohr sense. In the almost periodic distributions that we studied, the coefficients an and the exponents lambda n, they must satisfy the following properties. The sequence of coefficients an must belong to the Schwartz space of slowly growing sequences. That is, the growth of this sequence can be majorized by a polynomial. And for the sequence of the exponents, the sequence of exponents is real, and for sufficient large n, the growth is faster than c times n to the alpha, and alpha is greater or equal than 1. Here, in the studies linked to plates and beams, U is the displacement. In general, is something that we measure, like the displacement. Lambda n are natural frequencies or the eigenvalues of the associated eigenproblem, or to the problem. And an is associated to the unknown load that we want to identify. Now, if we have an almost periodic distribution with these characteristics, what can we assert? Let I epsilon be an interval of time of length epsilon. Then, given the sequence of exponents lambda, and if this sequence of exponents has growth of order n to the alpha, with alpha less than 1, then there is no epsilon such that u being equal to 0 in this interval, we can guarantee that u is equivalent to 0. That is to say, no matter we observe that u is 0 in this interval, no matter how long this interval is, there are always u that is not null outside this interval I epsilon. If the set of exponents lambda grows up to the order 1, that is order n to the 1, and is uniform discrete, that is, there is a number such that no two elements of the sequence of exponents can be closer than this number, then there is a minimum time interval length epsilon such that if u is 0 in this interval, then u is equivalent to 0. This is very parallel to the case of Fourier, ordinary Fourier series. We have an interval in which if the periodic function is 0, then the periodic function is equivalent to 0. Then, if alpha, the growth of exponents, is greater than 1, and lambda is uniformly discrete, and this is a very important condition, being uniformly discrete, then if there is an interval of length epsilon, arbitrarily small, if u is 0 in this interval, then u is forever 0. Moreover, there is a proposal of a numerical method to recover the coefficients of the almost periodic distribution. The coefficients an, we call, they are those that appear in this series. We have an and we have lambda n. Lambda n are the exponents and an are the coefficients that appear in the series that characterize the almost periodic distribution. our objective is to recover AN from the measurements that we make regarding U. Then, in this numerical method, we define a family of functions, phi, that has the very important property that is, its Fourier transforms are compactly supported in this interval. Note that the interval has length that is a multiple of a certain number tau. So tau is fixed, and then when k, which is a natural number, increases, the length of this time interval, which is where we make the observations in time, they grow. By using the phi functions, which have Fourier transforms that are compactly supported, as we have seen in this time interval, we make measurements of U and build a vector of which elements are called B. We define matrix elements Pmn by using the phi functions, but these phi functions, they are evaluated at the exponents of the almost periodic distributions. And we encapsulate the unknown coefficients an in another sequence of coefficients an. So we build a linear system of equations. An encapsulates the unknown coefficients an of the almost periodic distribution. Pmn are elements of a matrix which is evaluated using the phi functions. And B, the right hand side, is given by the measurements of the function U, the almost periodic distribution, tested over supports, compact supports, with this family of functions phi. Then we build an operator T that takes an, which encapsulates the unknown coefficients an of the almost periodic distributions, and it takes an to the measurements. So ours is an inverse problem. We have the measurements taken of U over compact supports, and then we want to identify an. Then we have a proof that this operator is injective. So we have uniqueness for the determination of coefficients an when we observe U over compact supports. When lambda n, which forms the sequence of the exponents of the almost periodic distribution, they grow with order at least 1, and they are uniformly discrete. So this is the almost periodic distribution. We identify an when we observe U, and we have uniqueness for the identification of an, the sequence an, provided the sequence of the exponents, they grow at least of order 1, and they are uniformly discrete. We observe that applying T can be interpreted as performing a product of a matrix of infinite order. That being said, we can truncate the matrix T and obtain a square symmetric matrix of order n, like this. Now we have the following result. There is a minimum number which is independent of the order of the truncated matrix n, such that the norm L2 of the matrix Tn is greater than this minimum number times the norm L2 of the vector x. And if we define a recover operator Rn as a composition of a truncation operator pi n, pi just truncates a sequence. We have an infinite sequence, we get a truncate sequences when we apply pi. And then when we apply the inverse matrix of Tn, which is an ordinary square matrix, then we get this recover operator, which is of finite order. Then we have this result that when n tends to infinite, that is the order of the truncated matrix tends to infinite, then the information regarding the observation of the displacement of the function u lets us to know enough information about the coefficients an. So when n tends to infinity, this evaluation tends to an. Now suppose that we have information regarding the function u corrupted by noise, and we have an a priori estimate of this noise in norm L2. Then instead of having the measurements, pure measurements, uncorrupted observations, we have observations that are corrupted by noise. We call it then tilde B. Then tilde B, the observations corrupted by noise, are BM, the observations with no corruption of noise, plus a term that depends on the error, measurement error in the observations. Then if we call the measurements that we make on the error, which of course are unknown, but we call them BE, then we get the following estimate. The recover of the coefficients, they are equal to the coefficients, target coefficients that we want to recover, plus a term related to the noise. And this term related to the noise can be bounded in norm L2. And this bound is very reasonable. It increases as the error level increases, and it decreases as the interval of time increases. Tau is related to the time interval, and k is a multiplier of this time interval. So as the time interval increases, the error that we get in the estimation of our true coefficients, they decrease. And also the error is related to the order of truncation. If the parameter n that governs the truncation, it increases, then the error that we get in our estimation, it also increases. It's very natural, it's very common in such inverse problems. Now we arrive at the last part of this presentation, where I show an interesting application of almost periodic distributions to a natural assembly of simple structural elements, which is the spider orb web. This picture was taken at the São Paulo University. São Paulo is exactly on the Tropic of Capricorn. It's a tropical place, and we have the opportunity to observe spiders. Not many, but we have the opportunity to observe them. This part of the presentation is based on two articles written with Professor Antonino Morassi. The first article we know of about the problem of how a spider might identify the location of a prey on a spider web was published in Nature. The author was Boyce, and the year 1880. Boyce remarked interesting things about the spider and about the spider web. I quote two passages. If the fork is not removed when the spider has arrived, it seems to have the same charm as any fly, for the spider seizes it, embraces it. And the other passage is, if the spider is not at the center of the web at the time that the fork is applied, it cannot tell which way to go until it has been to the center. In fact, the majority of spiders do not use vision, hearing, or olfactory senses to locate prey, although they have 8 eyes. The spider web has at least two main functions. They act as a catching device and also as a sensor device. And the main source of information about the position of a prey is obtained by the measurement of the vibration of the web. The mechanical model itself is new. It was proposed by Professor Morassi, Soler, and Professor Zaera. The equation, the differential equation that is related to it is also new. It's not the wave equation, it's not the plate equation, this is a different equation, and also it also deserved a simple study that was published in Mechanica. The result concerning spider webs can be simply put as the position and the footprint of the prey can be uniquely determined from the measurement of the transverse displacement taken on arbitrary small and thin ring centered at the origin of the web. Here is interesting to recall what Boyce wrote on Nature. If the spider is not at the center of the web at the time that the fork is applied, it cannot tell which way to go until it has been to the center. So the spider being at the center of the orb web seems to be important for the identification of the position of the prey. The mechanical setting is this. We consider the transverse vibration of the spider web under the external transverse force F, which depends on the position and the time. This force is caused by the prey. The orb web is put on a disc of radius r. It is centered at the origin O, and there is a concentrated mass at the center of the web. We assume that the load has this form. This is a product of a time function g and a spatial function f. This is the main equation of the problem. The main equation resembles the wave equation, but it's not. There is a singularity, non-removable singularity. It's not a regular singularity even at the origin. The displacement at the border is 0, and there is a special condition at the center, which reflects the Newton's second law. Our main result for the determination of the source, the spatial part of the source, from measurements of the dynamic response of the spider web is the following uniqueness theorem. For a given function g, which is the temporal part of the load, which is of class C1, with g different from 0 at time 0, if UF1 and UF2 are solutions to our identification problem corresponding to distributed force fields F1 and F2, then there exists a minimum time such that if the displacements over this ring omega for a sufficient long time, interval time of time 0 tau 0, then both loads F1 and F2 are equal. Here is important to note that we are using L2 functions because of the specificities of the mechanical model. This mechanical model cannot resist point loads applied at places different from the origin where there is our singularity. The main steps for the solution of the problem are: we set up an associated eigenvalue problem. Then we represent the load using the associated eigenbasis. We represent the solution of the dynamic problem cast into this eigenspace. And then we apply the results we have for the almost periodic distribution. By applying these steps, we arrive at three equations that are in fact almost periodic distributions. They are these ones. And the coefficients that we want to identify are these Fm, Fcm, and Fsm that are related to the load, spatial load that is caused by the prey. Then we apply the results for almost periodic distributions. And we got some interesting results, and here I present just one of them. What is the influence of the number of legs of a spider? Now I show the results. Here the spider hears the spider web for a tenth of a second. And this is the target load that is caused by the prey. This is what the spider hears from the spider web when it has 4 legs. Here it's what it hears when it has 6 legs, and then 8 legs, and then 10 legs, and then 12 legs. Of course, a spider has only 8 legs. From what we see here, when the spider passes from 4 legs to 6 legs, it gains much, very much. And from passing from 6 legs to 8 legs, it gains quite a lot of information also. But when it passes to 10 legs and then to 12 legs, it gains less and less information. So nature has its reasons to create spiders with 8 legs. Finally, I would like to thank the organizers and thank for you all for the attention. Thank you very much for your attention.
Thanks. As far as I understand, Professor Kawate, in Zoom, are there any questions?
And so, in all these applied problems, you use at some point a reconstruction of almost periodic function, something like this?
Yes, for the proof of both uniqueness and then for the reconstruction, you use the methods that are based on almost periodic distributions. That's right.
Okay, thank you.
May I ask a question? There are the question and the remark. As to the question, speaking about dealing with spider net, what mathematical model is in the use? Is it a graph with elastic edges or something like this? What is the model, exact mathematical model for the spider net?
It's a continuous it's a partial differential equation. That is, we made a continuous model for the real spider web. The spider web is made of rods, little lines, and then we made a continuous model. The
what is
partial
continuous
differential
model?
equation,
Is it a graph? What is the spider
no, it's
net?
not. It's not a graph.
Not a graph, but what?
Not a graph.
Okay, and what?
We model it as a partial differential equation. This is a linear partial differential equation.
What is the
but
object?
has,
Is it a membrane, something like membrane, or what?
Yes, like a membrane, but it's not a membrane because it has a singularity at the origin.
Okay, and just a remark which might be possible, might be useful. There is a book written by two Russians, Avdonin and Ivanov. It was translated in English in 19th. The book is called Families of Exponentials and Applications, something like this. And as far as I remember, I'm not an expert, but as far as I remember, the uniqueness theorems, there are a lot of results like uniqueness theorems, which you mentioned in the talk. Maybe it could be useful for you to look at this book, okay?
Yeah, thank you. Can you please repeat the name of the author?
The first one is Avdonin. Avdonin. And yes. Second one is Ivanov. Typically Russian family, yeah.
Thank you. Thank you very much for your suggestion.
Okay, thank you. Thanks again.
Thank you very much.
Oh, we have a dinner. Lunch.